Space has a background temperature of about minus 270 degrees Celsius. Leave almost anything there long enough and it should freeze. That sounds obvious. So why hasn't Voyager 1? NASA launched the spacecraft nearly 50 years ago. Today, it is farther from Earth than any spacecraft has ever traveled. Yet, it can still communicate with us across billions of kilometers. Because space does not cool things the way most of us imagine, the idea that Voyager should have frozen feels so obvious that most of us never stop to question it. After all, our everyday experience teaches us a simple rule. The colder the environment becomes, the colder everything inside it becomes as well. Leave a bottle of water inside a freezer, and eventually it freezes. Leave your car outside during a harsh winter night, and its engine becomes harder to start. Walk outside without enough clothing, and your own body begins losing heat almost immediately. Every experience we have tells the same story. Cold surrounds an object. Then the object becomes cold. So when we hear that deep space is almost minus 270 degrees Celsius, our brains instinctively extend that same rule to the universe. Voyager has spent decades surrounded by one of the coldest environments imaginable. Therefore, it should have frozen long ago. That conclusion feels almost impossible to argue against. But there is a hidden assumption buried inside that reasoning. Without realizing it, we picture space as though it were filled with an invisible substance, colder than any air on Earth. We imagine Voyager drifting through an endless ocean of extreme cold. That invisible ocean presses against the spacecraft from every direction, pulling heat away until every piece of metal eventually reaches the same temperature. That mental picture is completely shaped by life on Earth. It feels perfectly reasonable because it matches almost everything we experience on Earth. Here, every object is surrounded by matter. Air surrounds us. Water surrounds us. The ground touches our feet. Our everyday intuition was built inside that environment. Voyager was not. The farther it traveled from Earth, the less our ordinary experience became a reliable guide. To understand why Voyager never instantly became a frozen piece of metal drifting through the darkness, we first have to answer a much more fundamental question. What does it actually mean for something to become cold? Most people would probably answer that cold enters an object. It sounds strange when we say it out loud, but that is often how we instinctively picture it. A warm object sits inside a cold environment. Little by little, the cold moves in. Eventually, the object freezes. Physics tells a very different story. Cold is not something that flows into an object. What actually happens is much simpler. Energy leaves it. That difference sounds small. In reality, it changes everything. Imagine holding an ice cube in your hand. After a short time, the ice begins to melt. Most people would say the warmth from your hand melted the ice. That is exactly right. Energy moved from your warmer hand into the colder ice. Now think about your hand. It also became colder. Not because cold entered your skin. Your hand cooled because it lost energy. Left on its own, the net flow of energy is from the warmer object toward the colder one. The object losing energy becomes cooler. The object gaining energy becomes warmer. The same idea explains why a cold winter wind feels so much colder than still air. The air itself is not injecting cold into your body. Instead, fresh, cold air continuously carries away the energy leaving your skin. As soon as one group of air molecules warms up, the wind replaces them with new, colder air that can carry away even more energy. The process never has a chance to slow down. Water does the same thing even more effectively. That is why jumping into cold water cools your body much faster than standing in cold air. Water can carry away energy far more efficiently. Although these situations look different, they all depend on the same hidden ingredient. Matter. R is matter. Water is matter. Even the metal chair you sit on is matter. Tiny particles collide with one another. Energy passes from one particle to the next. The warmed particles move away. New, cooler particles arrive. The cycle repeats over and over again, without noticing it. This is the only kind of cooling most of us have ever experienced. That is why our intuition feels so convincing. Every freezer works this way. Every winter day works this way. Every cold drink works this way. So naturally we assume the universe works the same way. But the moment Voyager left Earth behind, it entered a place where that hidden ingredient almost disappeared. And once matter disappears, the entire problem changes. There is one difference between Earth and deep space that matters more than almost anything else. It is not temperature, it is matter. Here on Earth, matter surrounds everything. Air, water, and solid materials constantly exchange energy with us through countless microscopic interactions. Everyday cooling depends heavily on matter carrying energy away. Space is different. When Voyager left Earth, it did not enter an ocean of freezing air. It entered almost nothing at all. When people say deep space has a background temperature of about minus 270 degrees Celsius, they are not describing an invisible gas surrounding the spacecraft. They are describing the incredibly weak background radiation that fills the universe. That is a very different thing. Voyager is not floating inside a giant freezer. It is floating inside an almost perfect vacuum. And a vacuum changes everything. There is almost no surrounding matter to carry energy away from the spacecraft. There is no cold wind sweeping across its surface. There is no freezing gas touching its metal panels. There is no icy fluid flowing around its instruments. The two most familiar ways objects lose heat on Earth, conduction and convection, have almost disappeared between Voyager and its surroundings. That does not mean Voyager cannot cool down. It absolutely can, but it must do so in a completely different way. Imagine standing beside a campfire on a winter night. Even without touching the fire, you can feel energy reaching your face as electromagnetic radiation. The fire is continuously sending energy outward. Now imagine running that process in reverse. Instead of receiving radiation, Voyager is constantly sending it away. Every object with a temperature above absolute zero emits electromagnetic radiation. People do it. Animals do it. The Earth does it. The Moon does it. Voyager does it as well. This process is called thermal radiation. Unlike conduction or convection, thermal radiation does not need air. It does not need water. It does not need any surrounding matter at all. Energy simply leaves the spacecraft as electromagnetic waves and travels through empty space. That is how Voyager loses heat. At first, that sounds like bad news. If Voyager has been radiating energy into space for nearly half a century, shouldn't it have become colder and colder until everything froze up? Only if that were the entire story. It is not. Losing energy is only one side of the equation. Voyager is also producing energy from within itself. That is where one of the spacecraft's most remarkable engineering systems enters the story. Unlike satellites orbiting close to Earth, Voyager cannot rely on large solar panels. By the time it reached the outer planets, sunlight had already become far too weak to provide enough electrical power. Today, in interstellar space, sunlight contributes almost nothing. Instead, Voyager carries its own long-lasting source of energy. Hidden inside the spacecraft are radioisotope thermoelectric generators, often called RTGs. Their job is frequently misunderstood. Many people imagine them as unusual batteries. They are not batteries. They begin with heat. Inside each RTG, plutonium slowly undergoes radioactive decay. That natural process continuously releases thermal energy. Special devices convert part of that heat into electricity. The rest remains heat. In other words, Voyager is carrying its own tiny, steadily glowing heat source through interstellar space. That electricity powers the spacecraft's computer, radio transmitter, scientific instruments, and onboard systems. Almost all of that electrical energy eventually becomes heat as well. The computer warms slightly while operating. The electronics warm slightly while operating. Even the transmitter releases heat while sending signals toward Earth. Energy is constantly moving through the spacecraft. Some of it escapes into space through thermal radiation. Some of it remains inside long enough to keep critical systems within their operating temperatures. That means Voyager's temperature is never determined by one number written on a thermometer somewhere outside the spacecraft. Its temperature is determined by balance. How much energy enters the system? How much energy is produced inside the system? And how much energy escapes into space? That balance, not the background temperature of space, is what decides whether Voyager stays warm enough to keep working. This is the challenge NASA has been solving ever since Voyager left Earth. The engineers were never trying to protect the spacecraft from an endless ocean of freezing cold. They were trying to manage the flow of energy. Every watt produced inside Voyager has a job. Some of it powers the computer that keeps the spacecraft functioning. Some of it powers the radio transmitter that sends faint signals back toward Earth. Some of it powers the scientific instruments still exploring interstellar space. And almost every bit of electrical energy eventually ends up as heat somewhere inside the spacecraft. That heat is not a waste product. It is part of the spacecraft's survival. Without enough internal heat, temperatures inside Voyager would gradually fall until critical systems could no longer operate safely. But keeping that heat is just as important as producing it. If energy escaped too quickly, Voyager would cool faster than its power system could replace the lost heat. If energy became trapped too effectively, certain components could become hotter than engineers intended. Long before Voyager ever left Earth, NASA's engineers had to design a spacecraft capable of controlling both problems. Layers of insulation slow the escape of heat into space. Heat also moves through the spacecraft by conduction, helping redistribute energy between warmer and colder areas. Thermal control keeps critical systems within safe operating limits. Nothing about Voyager's thermal system is accidental. Every design choice exists because energy is constantly moving. The spacecraft never reaches a point where heat simply stops flowing. Instead, it eventually settles into a balance. As long as the energy being produced and retained is enough to replace the energy radiated into space, Voyager remains warm enough to function. That is the real reason it survived for nearly half a century in deep space. Not because space is warmer than we imagine. Not because someone secretly installed an enormous space heater. But because the spacecraft was carefully designed around the physics of energy transfer. By this point, the original mystery has almost completely disappeared. The question is no longer why minus 270 degrees Celsius failed to freeze Voyager. The better question is whether Voyager can continue maintaining that balance forever. The answer is no. Not because deep space is becoming colder. Deep space today is essentially no colder than it was when Voyager crossed the orbit of Jupiter or Saturn. or Neptune. What changes is Voyager itself. The source of energy inside the spacecraft slowly becomes weaker. At the heart of each RTG, plutonium continues its natural radioactive decay. That process is remarkably reliable. It can continue producing useful energy for decades. But it never remains constant. Year after year, the amount of available electrical power slowly decreases. The change is gradual, almost too gradual to notice from one day to the next. But over decades, it becomes impossible to ignore. Every year, NASA has a little less electrical power available than the year before. That creates an entirely new engineering challenge. If there is less electricity, not every system can remain turned on. Engineers must decide which instruments continue operating and which ones must be switched off forever. Over the years, Voyager has gradually become quieter. Scientific instruments that once explored magnetic fields, charged particles, and plasma have been shut down one by one. Not because they stopped working, but because the spacecraft could no longer afford the power required to keep everything running at once. Every instrument that is turned off saves precious electrical power. Every watt saved helps extend the mission a little longer. There is another consequence that is much easier to overlook. When electrical systems consume less power, they also produce less heat. The spacecraft is not only losing available electricity, it is also slowly losing part of the internal warmth that helped maintain its thermal balance. That means NASA is constantly balancing two connected problems at the same time. How to keep enough electrical power for communication and science, and how to keep enough heat inside the spacecraft for its most critical components. Those two challenges are inseparable. The spacecraft does not simply need electricity. It needs the flow of energy that electricity creates throughout its entire structure. Eventually, that balance will become impossible to maintain. Not because Voyager suddenly reaches a colder region of space, but because the energy available inside the spacecraft will no longer be enough to support every essential system. One day, there will not be enough power to operate the transmitter that has spent decades speaking across the solar system. The stream of data arriving on Earth will finally stop. The last signal will leave Voyager, travel across interstellar space for many hours, cross billions of kilometers, reach Earth, and then there will be silence. But silence does not mean the journey is over. The scientific instruments may stop making measurements. The computer may eventually shut down. The transmitter may never send another message home. None of those things will stop Voyager itself. The spacecraft does not need electricity to continue moving. It only needed electricity to think, observe, and communicate. Its motion was given to it long ago by the rockets that carried it away from Earth, and by the gravitational slingshots that accelerated it past the giant planets. Once those encounters were over, Voyager no longer needed continuous thrust to keep moving forward. In the nearly empty vacuum between the stars, there is almost nothing to slow it down. Long after its final transmission has faded into history, Voyager itself will continue its quiet journey through interstellar space. The strange thing is that the spacecraft never violated the laws of physics. It revealed how easily our intuition can mislead us. We imagined deep space as an unimaginably cold ocean waiting to freeze everything inside it. Instead, Voyager taught us something much more interesting. The temperature surrounding an object does not automatically become the temperature of the object itself. What matters is the balance of energy. How much energy an object receives, how much it produces, how much it loses. That balance determines its temperature, not a single number describing the emptiness around it. And perhaps that is Voyager's most remarkable lesson. Even after its scientific instruments fall silent, it will still carry that truth across the darkness between the stars. In deep space, temperature was never determined by cold alone. It was determined by the flow of energy,